In section 4.2, we looked at analytic solutions to the mass spring damper system. Okay, we looked at analytic solutions, which required us to use the complexification method. All right, so we have a good idea of what some of our solutions can look, what they can come out to look like. They can have exponentials, so they can have damping. There could be some steady state in the solution. So this is what in 4.3 we are trying to kind of get an idea about what's going on with the qualitative behavior. Qualitatively, what's going on. Okay, so we're focusing on the differential equation as above here, and we're limiting our forcing function to be of the form just a cosine omega t. So a is the amplitude of the forcing function, okay, and capital omega is the frequency, sometimes called the driving frequency or the forcing frequency of the oscillations. Okay, what we'll see is that there are a variety of cases that we can look at, okay, and understand the qualitative behavior. And the first case is to break the problem down into damping the delta term being equal to 0. So if what we have here is a lot of parameters in this problem. We can change the amplitude of the forcing term, you can change the frequency of the forcing term, you can change the natural frequency of the mass spring system, and you can also control the delta term. And so each one of those terms, A, capital omega, little omega, and delta, becomes a slider bar that can be adjusted, okay, in this model. And what we are seeing is the solution to the differential equation with the initial conditions zeroed out. Okay, so that's what we're seeing in this plot right here, is the solution to the differential equation with 0 initial conditions. So my claim is that in 4.3, we would like to focus just on the case where damping the delta term, we zero it out. And then we look and see what can happen to the solution. And what we're trying to focus on is qualitative behavior. Here I'm just looking at the solution for enlarging the solution for more time. So I've gone from time 0 to 12 now. And we're seeing that the solution is just oscillating up and down, okay, for the value of omega, capital omega, to be 2. Okay. But look, no matter how I change omega here, right, we seem to get these oscillations which keep happening, right? If I change the amplitude of the forcing term, the only thing that's changing is the bar over here showing that the oscillations are getting higher and higher amplitude. So changing the A term isn't really changing what the solution looks like. It's still kind of oscillating a lot. If I change the frequency of the natural frequency of the spring, notice that we're starting to get some change in behavior, but there's just a lot of oscillations happening. Okay, so really not a qualitative change in the behavior, right? If I change omega, still got a lot of wiggles, okay? But the important case here, when delta is equal to 0, you just get lots of squiggles. Your solution to the differential equation is just going to look like a bunch of oscillations. Okay, that's in general what happens. But something special happens. So what happens in general is just these kind of wild oscillations. Okay, but there is one special case which happens to the oscillations when the natural frequency omega and the forcing frequency get to be close to each other. So if you can see this number here, it's about, we'll change it to 3, okay? And as the forcing frequency gets close to the number 3, right now it's 2.5, let's make it 2.6, let's make it 2.7, oops, let's make it 2.7. You can see that something started to happen. Instead of these wild oscillations, it looks like there's starting to be some grouping that's happening here, right? And so it looks like these oscillations start to come into packets, okay? 2.8 is if I get closer to the forcing frequency is getting closer to the natural frequency. 2.9, you can see that these little packets start to form, okay? So that's kind of something special that happens to these oscillations, that they get to be these oscillations and then they get small and then oscillations pick up again and then they come in little packets. Okay, this is what's called the beat. You get beats that are happening. Okay, when they pinch down into these little bits, that's called the beats. Okay, and this is happening when the forcing frequency is getting close to the natural frequency of the spring. Okay, now if omega gets farther away, we just kind of go back into the case where the oscillations are just kind of wildly oscillating. Okay, so when damping is equal to 0, the only special thing that happens, the only change in the behavior of the oscillations, is when you get the beating phenomenon happening. And the beating phenomenon occurs when the frequencies are getting close to each other. Okay? If the frequencies are exactly equal to each other, okay, we will have to see notice that the computer had some trouble plotting them, and we need to look and see why that happened. Okay, so for example, if it was getting really, really close, okay, look what's happening. That the oscillations are getting larger and larger and larger. So the oscillations are getting unbounded. So that is the other case that can happen when the forcing frequency is close to omega, you get beats. But when the forcing frequency is equal to the natural frequency, this is the case that's called resonance, right? And the oscillations get to be larger and larger, and the oscillations eventually get too big, and you can break your mass spring system at that point. Okay, so that's one of the qualitative behaviors that happen when delta is equal to 0. So going down the branch where delta is equal to 0, two different phenomena, the resonance and the beats occurring. Okay, in the next video we'll take a look at the analytic behavior behind what analyzing qualitatively the beats and the resonance structure of the mass spring system.